All right, guys. So I came to know that the previous video I had recorded for gain bandwidth product did not have the screen shared. So I'll teach the gain bandwidth product again with the Lab 5 hints. Okay. So let's see what Lab 5 is about. In Lab 3, we learned how to build a inverting amplifier and a non-inverting amplifier, correct? And then in Lab 4, we learned how to use an op amp to add and subtract. And also at the same time, we also learned about the voltage followers, correct? Now in Lab 5, we basically would see how to create or how to build integrators and differentiators using op amp, okay? So what you see right here is a kind of inverting configuration, correct? It's just that you're using a capacitor instead of a resistor from what we have in Lab 3, right? And if you derive the transfer function for this, this is what the transfer function looks like, right? And if you remember the Laplace transform, 1 over s times x of s, right? If you do an inverse Laplace, would basically come down to integral 0 to infinity x of t dt, right? So multiplying with 1 over s in Laplace domain is nothing but integrating, right, in the time domain. So with that, we can actually see that this is an integrator because you are taking vi of s and you're multiplying with 1 over s, right? So if you try to convert this into time domain, your v naught of t would literally be minus 1 over r1c, correct, times integral vi of t dt. But practically, there is some difficulty with this circuit, and this paragraph clearly explains what it is. And let me just briefly go through it. So if you remember in Lab 4, we measured something called input offset voltage. Even though we are not actually using the op amp, there is a good chance that there will be some DC difference, right? It can be 1 millivolts, 2 millivolts, however small it is, but there will be some difference. And if you see this integrator behavior, right? If I substitute s equals to 0, the gain of this transfer function is literally infinite. So the output will just blow up or otherwise saturate at the maximum voltage, which could be plus 5 volts or minus 5 volts, depending on the sign of the input voltage difference, right? And we saw that it's inevitable because practically there is always some error or some kind of offset voltage there, right? So however small it is, it could be 1 millivolt or even smaller, but the gain is so large that it will always saturate. So even before we actually try to apply our inputs, the output is already saturated, correct? So to rectify that problem, we do the following. We add one more resistor to the circuit, right? Here we add one more resistor and we get this transfer function. So if you look at this transfer function, we see that if we substitute s equals to 0, right, we have a regular gain of negative R2 over R1. And if you have an input of say 1 millivolt, correct? And if the gain is say like 3 or 4, the output will just have an offset of 4 millivolts or something, which does not affect our regular measurements, right? So this is called lossy integrator circuit because this resistor actually takes some voltage drop, and this is why it's called lossy integrator circuit. And this is the pure integrator circuit that would have worked if the input offset voltage were not to exist. So ideally, this is the pure integrator, but practically it doesn't help much, okay? So this is what we're going to build in our lab, a lossy integrator circuit, right? And mathematically, I see a lot of people don't understand what an integration means. If you have a random function, right, integrating it from time t1 to t2 is nothing but area under that curve from T1 to T2, right? So if I'm asking you to integrate, for example, a sine wave running over 0 volts, so I'm basically asking you for the area under that curve. And because it has equal amounts of positive areas and negative areas, the integral of a sine wave over whole time period is 0. Okay. And if you're trying to integrate something like, say, a square wave, which does not go on the negative side, right? So let's just say it's a positive side square wave. Now, if I try to integrate it over whole time period, correct? So this is T by 2, this is T. This portion has an area of A times T by 2. And this portion has an area of 0. So if I try to integrate this square wave over whole time period, I get answer AT by 2. Okay, that's just a mathematical understanding of what an integrator is. All right, next we move on to a differentiator. Okay, so differentiator is also, we are using an inverting configuration. So instead of a resistor in lab 3, we have a capacitor here, and we get this transfer function. Again, in Laplace transform, if you multiply some function with S in time domain, so if you take an inverse Laplace to get the time domain, we're basically asking you to differentiate that function in the time domain, correct? So if you see here, we are multiplying Vi of S, correct, with S. So the time domain representation of this would be Vi of t equals negative CR1 times d by dt of Vi. Correct? Excuse me. So it does what it's supposed to do. But again, if the op-amp were to be ideal, this works. But what if the op-amp is not ideal? Again, we have a similar problem to what we have in integrators, right? So what if there is something like a high frequency noise, right? So noise is a very small amplitude, but it has a very high frequency, correct? So you'll see that at very high frequency, this has a very large gain. So the noise will be amplified a lot, correct? So to fix that, we basically do something similar to what we did. We put a resistance in series to get this transfer function. Okay. So now at very high frequencies, this does not have an infinite gain, but it actually flattens out. So if I try to draw a Bode plot for this, I basically have, so at higher frequencies, the gain just keeps going on. But this transfer function starts like this, but flattens out at high frequencies. So at high frequencies, instead of the gain blowing up, we try to make the gain a large value, but a constant value. Okay. So that's how we fix the problem that we get using a differentiator, and it's called a pseudo differentiator. Okay. I want you guys to go through the theory portion that is in integrator and the differentiator to understand in more detail as to what the problems occur in integrators, and at the same time, the problems that occur in the differentiator. Okay. Now, there is one more non-ideality that comes in the op-amps, that is a finite gain bandwidth. Okay. Let's quickly go ahead and talk about what it is. All right. So if you consider that an op-amp is ideal, this is what we do, correct? So let's just consider this as an ideal op-amp. Okay. So ideal op-amp, we basically say that it has a very large gain, practically infinite, correct? So A here is infinite. And let's say that I'm operating this op-amp in an open loop condition. When I say open loop, I'm basically not giving any feedback. correct? So I won't have any feedback of any sorts, and let's see what it does. So the output V out will just be A times V plus, correct, minus V minus. And because A is very large, which is basically infinite for ideal op amps, right? We basically say that the V out will always saturate to either plus 5 volts or minus 5 volts, however small this difference is, correct? But practically, the gain is not infinite, but the gain is a very large number. So A is not infinite, but a very large number, something like say 10 to the power of 5, 10 to the power of 6 or something. So based on that, you'll get the output you want, correct? And this is still with ideal assumptions. So ideal assumption is basically saying that the op amp has a very large gain, which is constant irrespective of the frequencies you're operating at, correct? So if I just ground this terminal and give a sine wave input, I'm going to get an output which is 8 times the gain, 8 times whatever sine wave I give here. So let's say 2 sine omega t is what I'm giving, right? So we'll just get 8 times 2 sine omega t. But once I say that the op amp is no longer ideal, which is usually practical case, correct? The practical case, the gain is not constant, but the gain actually goes down with the frequency. So this is an open loop op amp's Bode plot. Keep in mind that I'm still discussing the op amp itself. I'm not building any feedback across it. So the circuit is just this, plus, minus, right? I'm grounding this, I'm giving a source over here, and I'm just taking the output. That's it. There is no feedback of any sort. If I draw the Bode plot of an actual op amp in practical scenarios, you see that the gain is very large, like 10 to the power of 5 or something, right? And you expect that it just goes straight, because that's the ideal assumption, right? So the output is just 20 log 10 to the power of 5, which is the gain. But in practical scenarios, it starts there, but as the frequency increases, the gain actually starts to go down. So it's only constant until very small frequencies like 10 hertz or something, right? So now we know that 10 hertz is the 3 dB frequency of the open loop op amp. So beyond 10 hertz, if you're trying to operate, we are just losing gain as we try to operate at higher and higher frequencies. So practically, an open loop op amp does not have a lot of advantage in the labs or in practical environment, because the higher and higher frequencies you want to operate at, the gains are lower and lower. I mean, we can see that, maybe at like 100 kilohertz or something, you still have some gain, say like gain of 2, 3 or something, which is okay for an undergraduate lab or something. But practically, that's not the gain you want. You want a very large gain, correct? So let's try to see how this looks like in the transfer function sense. So if I'm trying to write an open loop op amp's transfer function, OL stands for open loop, just for the notation, you can see that, let me call this very large number A naught. Okay, so let me go back to regular scale for a second. Okay, let me not work with decibel scale right now. So let me call this large number A naught. So that is the DC gain of an open loop op amp, because that's the gain at frequencies 0 or frequencies which are very small. So the transfer function looks like A naught, which is the DC gain over 1 plus S over omega naught. Right? So this is how the transfer function of this Bode plot looks like, the one in the red, where omega naught here is nothing but 2 pi f naught, which is the 3 dB frequency, which happens to be 10 hertz in the example I took. It could be 5 hertz, 7 hertz, whatever, based on the op amp's data sheet. But for this example, I'm choosing the 10 hertz. So we know that this is a first order low pass filter kind of a behavior. That's how the op-amp behaves, right? So like I said, the main problem with open loop op-amp is that the bandwidth is literally very small. You cannot, or you don't want to operate beyond bandwidth, because see, I couldn't actually get a gain of 10 to the power of 5, but even if I work with a something say like 1 kilohertz, right? So that is like 2 decades away, because 1 decade is 100 and the next decade is 1000. So I'm already losing about 40 decibels, correct? So this so this is 100 decibels, right? From 100 decibels, I am basically coming down to 60 decibels. So just if I want to operate at 1 kilohertz, I'm losing about 40 decibels of gain, which is not quite good. So I want to build amplifiers which has higher bandwidths, basically something like until here or something, so that I can actually have higher gains until that frequency, right? So how to do that? That is where our closed loop behavior comes into picture. So let's quickly try to consider okay, it's stuck. Some things are. Let's quickly try to consider a few configurations, right? Like non-inverting or inverting configurations, and see what's actually doing. All right, so I hope you understood what we just were talking about. So let me try to summarize what we talked. So we basically said that the open loop transfer function of an op-amp looks like A naught over 1 plus S over omega naught, correct? Where the body plot looks like this. The gain is A naught in a linear scale, or 20 log A naught in decibel scale, correct? And it just starts going down at frequency omega naught, which is a very small frequency, correct? So we are trying to use this op amp in an open loop scenario to increase the bandwidth, right? So, sorry, closed loop. So the main advantage of closed loop scenarios is that we have higher bandwidths. And you'll observe that if you know how the op-amp behaves in the open loop scenario, which we just saw, we know everything about the closed loop scenario. Let's quickly see how that happens. Let's take first case, which is non-inverting case, right? For non-inverting, we basically have the input going to the positive terminal and a feedback like this. Or if I try to redraw it the way the lab tells you or the course tells you, these both are the same thing. It's just redrawn in a different fashion. Okay, so let's call this R1, let's call this R2. Let's see what advantage this circuit brings in. This is no longer open loop because we actually have a feedback, right? Coming back from the output back to the inputs, right? Now let's try to derive the non-ideal scenarios, because you already have derived it for ideal scenarios where V out over V in comes out to 1 plus R2 over R, right? See that the gain is just constant. It's not frequency dependent at all. It's just a constant value. But we just are trying to analyze how the op amp would behave if we inculcate the frequency dependency behavior, correct? So let's write the equations for it. Once we say that the op amp is non-ideal, the assumptions that we have for ideal op amp changes. Because for ideal op amp, remember for ideal op amp, if we have a feedback loop, the first assumption we do is that the V plus and V minus will end up having the same voltage, correct? And second one, we say that the input current is 0, right? And third one, we say that the gain is constant and very large. If you're trying to work with a non-ideal case, the first one is no longer valid, right? Because this only happens when the gain is like, very large and constant and infinite or whatever. So V plus is no longer equal to V minus. We cannot make that assumption. This one is still valid because the input impedance of the op-amp is still very large, close to mega ohms or something. So we can still say that input current is 0. Right? And third one is no longer valid because the gain is not constant, but the gain is actually frequency dependent. Okay, so these are the non-ideal assumptions. So let's try to quickly solve it using non-ideal assumptions. So we have a non-inverting configuration. This is our V in. This is our R1, R2, right? So we cannot, so if this is V in, we cannot say that this is also V in. So let's just call that Vx. Okay, so this is our V out. So the first equation I'm going to write is a regular KVL. Wait, did I have a right circuit? Give me 1 second. I believe I have the right circuit. Yes. All right. So the first equation will basically be the same current equation because there is no current that flows into the op-amp. All the current that's being drawn from the ground has to go to the output, right? So the first equation would be that the current in R1 equals to the current in R2. The current in R1 is 0 minus Vx over R1. That is equal to the current in R2, which is Vx minus V out over R2. That's our first equation. And the second equation is just the op-amp's equation. Remember, the gain of this op-amp is no longer A, which is constant, but it is an actually open loop gain. That's the property of the op-amp. So the V out is not A times the difference of the input, but it's actually open loop gain, which is frequency dependent, times the input difference, which is V in minus Vx. Okay, so if we solve this both, which I did before the class, so let me just copy the final equation or show you the math over here. Right, so see that this is our first equation, this is our second equation, and finally, if I try to solve it, this is what I get. Okay, so let me just copy that over and let's do a little more analysis as to what it is. I think I copied it. All right. So sorry, I don't think I did. Okay, let me just write it down. So what we get is that V out of S over V in of S equals, after rearranging, I think it will be 1 plus R2 over R1 over 1 plus, I believe, what was that? One plus R2 over R1 times 1 over open loop gain. Right, so this is what the expressions come down to. Okay, now before I do a little more analysis on this, let me talk a little more about what's happening in the open loop case. Okay, so if I take the open loop case, so what I'm trying to analyze a little more is about the open loop case. We have the transfer function. right? Now we are more interested to see what happens in high frequencies, because we said omega naught is very small, so it's not useful at all in small frequencies. So at high frequencies, if you remember the approximations I used to do in complex numbers, in high frequencies, the S term, which is S equals to J omega, will be very large. So because S is very large, I can discard one with respect to this. So at high frequencies, the open loop transfer function will approximately look like A naught omega naught over S, which is A naught omega naught over J omega. Correct? So this is nothing but a linear behavior with respect to frequency in decibel axis, correct? So this is basically a straight line with slope negative 20 decibel per decade, right? And if you see what happens at low frequency, the S is not large enough. So we basically ignore S over omega naught with respect to 1 because it's very low frequencies. So the H open loop just behaves like a constant value A naught. So this is how the low frequency value behaves. All of this happens at omega, right? So just keep in mind how the high frequency behaves. All right, now let's take this transfer function and do a little more analysis for the non-inverting amplifier. So this is what we have for the non-inverting amplifier, correct? So for non-inverting amplifier, after doing the non-ideal analysis, we have input over here, right? This is R1, this is R2. We have the output over input look like 1 plus R2 over R1 over 1 plus R2 over R1 times 1 over H open loop of S. Okay. Now we are interested to see what happens to this transfer function at low frequencies and what happens to it at high frequencies. So at low frequencies, remember that the H open loop of S behaves as a constant value A naught, which is very, very large, right? So because this is very, very large, 1 over H will be very, very small. So this, all of this will be very small when compared to 1. So we can just ignore it at low frequencies. So at low frequencies, the transfer function V out of S over V in of S, which is less the closed loop behavior, correct? Is nothing but 1 plus R2 over R1. And remember, this was the ideal gain of this configuration, right? So if you start drawing the Bode plot, we expect the Bode plot to be constant at a gain of 1 over R2 over R. And if you remember from lab 3, we had a gain of 6, which is about 15 decibels, correct? But this will not be constant throughout all the frequencies. So let's see what happens at high frequencies. At high frequencies, the H open loop, how does it behave? We just saw that at high frequencies, it behaves as A naught omega naught over S. So if I rewrite the transfer function, it will look like 1 over R2 over R1 over 1 plus R2 over R1 times, right, S over A naught omega naught. Correct? If you see, this is just like a first order behavior, right? So let me call this the closed loop gain, correct? That's the ideal case closed loop gain, right? So 1 plus R2 over R1 over 1 plus S over A naught omega naught over 1 plus R2. Just a little rearrangement. So how does this look? It will start here, correct? And it goes down once it reaches this frequency. A naught omega naught over 1 plus R2 over R. Let's see what happens to this at high frequency. At high frequency, S is very large, so I can ignore 1 with respect to that. And we basically get this cancel out, and we basically get A naught, omega naught, or S at high frequency, correct? Does this not look familiar? This looks exactly how an open loop op amp behaves at high frequency, correct? So the learning outcome is that if we know the open loop op amp's behavior, which is like this, remember, it only had a very small bandwidth, like some 10 hertz or something. And we know that the gain of the open loop op amp is A naught, which is like very large. And if you're trying to build a non-inverting amplifier configuration using this, which has a very small gain, something like say 1 over R2 or R, right? It so happens that at all the low frequencies, it behaves constant. And once it reaches this frequency, it just follows the open loop op amp's behavior. So if you want a different gain, it will start like this and just follows this behavior, right? And this frequency is particularly A naught omega naught over 1 plus R2 over R. And this is A naught omega naught over whatever gain you have, 1 over R2 or R1. So let's call this a different value so that value will come here. Okay. And why is it called gain bandwidth product? See that in the open loop, we have very high gain, but a very small bandwidth. Now, if I try to sacrifice the gain, now I'm trying to operate at lower gain, I'm actually getting a very high bandwidth. So it's called, it's a trade-off between gain and bandwidth. If I need very large gain, I have to sacrifice the bandwidth. If I need very small gain, I can have very large bandwidth. Now remember this is how it behaves. The open loop behaves at high frequency, correct? So if I try to take the gain of that open loop transfer function, what would I get? I'll get magnitude of this, which is nothing but A naught omega naught over omega. So the gain of the open loop times the frequency is a constant value, A naught omega naught. So this is called the gain bandwidth product, which is a constant value and which is a property of the open loop op amp. Keep that in mind. So once you have the open loop op amp's body plot, if you know the A naught, if you know the omega naught, you know the gain bandwidth product. And it so happens that on this line, if you know another gain, its corresponding bandwidth will also have the same product, because we just saw gain times bandwidth on this line anywhere is also equals to A naught omega naught. So given we are taking gain A1 has a bandwidth omega 1, this will also be equals to A1 omega. If you take A2 and it has bandwidth omega 2, this will also be equal to this, right? And now if we come to the non-inverting configuration, we observe that once it hits this point, right, it follows the same behavior as an ideal op amp. So in this region, if you want to operate with a different gain, say G2, and say if its corresponding frequency is omega 2, right? If you know one of this, we can just find the bandwidth if you know A naught omega naught. Because we just saw that at high frequencies, we have this. So a gain at high frequencies times omega will be equal to the gain bandwidth product for the non-inverting configuration as well. Does that make sense? So the conclusion is that if you know the open loop op amp's body plot, essentially knowing the A naught and omega naught. I mean, this is in radians. If you want to know in frequency, all you have to do is divide this omega naught by 2 pi, and you will know frequency, F naught. And if you're trying to build a non-inverting configuration of a specific gain, say A1, you already know the bandwidth of this. If you want in frequent hertz, it is omega 1 by 2, because A1 times this will be equals to A0 times this. Does that make sense? And see that because I'm sacrificing the gain, I'm getting higher bandwidth. And if you pick any gain, you'll get corresponding bandwidth. Now, if I pick a gain 1, what happens? I get specific frequency. Let's call it unity gain frequency. So this should, the product of these two should also be equals to A0 omega naught, right? So 1 times FU equals A0 F0, or 1 times omega U equals A0 omega, whichever you want to use, correct? And because it's just 1, the unity gain frequency itself, I can call it as gain bandwidth product, right? That's why gain bandwidth product is otherwise also called unity gain frequency, only because 1 times the frequency is also equals to A0 omega. Okay, so that is with non-inverting configuration. Okay, now if I just scroll back and I'll show you the work on inverting configuration as well. So if I do the inverting configuration, I did the math over here. Okay, so this is the inverting configuration. We have the same non-ideal assumptions where these two cannot be the same voltage, and I did all the math. See that this is the non-inverting formula. See that it shares a pretty similar structure. The denominators are the same. Just the numerator has the ideal gain that you get when you try to solve it as an ideal op-amp. So because the denominators are equal, the pole frequencies are the same. So the inverting also behaves something similar to what the non-invertings behave. I mean, it comes with a small approximation, but overall, you can actually do some. You can look at the work. You can pause here, look at what I worked with. So this is the transfer function. I'm doing the same low frequency approximation, which looks like an ideal gain of negative R2 or R1. And I'm doing the high frequency approximation, which looks like this. So at high frequencies, the S is very large. So I can ignore 1. And I come to this expression. Here I make one more assumption that R2 or R1 is pretty similar to R2 or R1 plus 1. So this looks pretty similar to what we have for non-inverting case, right? So all we have to know is that in conclusion, if you know the open loop op-amps body plot, if you're trying to build a amplifier of a specific gain, you already have access to the frequency because you already know the gain bandwidth product. Okay, now what if I want a very high bandwidth? What if I want a very high bandwidth? I basically have to operate at very small gains, correct? What is the workaround for this? Like, how can I have higher gains and also higher bandwidths? What you do is that you take this op-amp and you put it in cascade. Right? That way, the bandwidth is higher and the resulting gain is gain time G1 times G2. If the first setup has gain G1, the second setup has gain G2, the final gain will be G1 times G2. And if you actually multiply the transfer function, so let's say the transfer function of this is A0 over 1 plus S over omega naught. The transfer function of this is also 1 over S plus omega naught. And if you multiply this, find the gain, and equate the gain to 1 over square root 2, you'll find the 3 dB frequency, and the 3 dB frequency will be your bandwidth, correct? So you'll see that the bandwidth will be higher and the gain will also be higher. Okay, so that's the takeout from gain bandwidth product. Let's see what else lab 5 talks about. So lab 5 talks about that. So we just saw that, and you'll actually be measuring the gain bandwidth products in measurements. Okay, and now there's something called slew rate. Slew rate is again the rate at which a signal can change, right? So let's go back to sharing the screen. So if you have an op-amp like this, right? Say I'm suddenly changing the input. Say I'm giving a step response. The output does not immediately change. It actually takes some time to change. So the output may not look exactly like a square increase, but it may look something like this. Right? Now, what if this op-amp is very, very slow? It may actually not look like a square function at all. So we want to know what's the slew rate of a specific op-amp. How fast does it change? Does it change fast like this, or does it change very slowly like this? Right? We always want something that changes faster because it is a very sharp change in the input. But practically, the very sharp change is not possible, so we settle for something which is fast enough. Right? So how do you find the slew rate? So if you take a sinusoidal wave, something say a naught sine omega t, right? So if you differentiate this, because that will be the rate of change of the signal, which is a naught omega naught sine cos omega t, correct? So the maximum rate of change of this signal will be a naught omega naught when cos omega t is 1, correct? So this is the maximum rate at which a sine wave changes, right? So we try to accommodate an op-amp to have at least this much maximum slew rate. Okay, so it can either accommodate at some frequency, we can either have a high change in amplitude all of a sudden, or for a fixed amplitude, we can have high frequency change. Okay, so that's what a slew rate accommodates. Okay, all right, now let's see what you have to do in lab 5. In lab 5, for the first question, for the lossy integrator, derive the time domain equation for the output in terms of the input. Okay, so if you see the lossy integrator, this is what we have, right? So this is in a Laplace domain, and it's asking you for output if you in the time domain, right? So it's basically saying that, so remember that all of this are in Laplace domain, not in time domain, right? So what I would recommend is that you can make an approximation saying you're operating this at high frequency so that this transfer function sort of looks like this transfer function, right? And remember, I already explained how this one looks in time domain. It's just the integral of the transfer function, so integral of the input with some constants multiplied, right? So you can either do that. You can either say it will be an inverse Laplace of this, right? Or you can say this, and then you can say that the time domain is just the integral of the signal, right? All right, so that will be your first question. And then you have to find the resistance value that actually gives a gain of this, correct? And you have to sketch the Bode plot. You have to find the output for a given input. You already have the access to transfer function, and you already did this in lab 1 and lab 2, finding the output given an input and the transfer function. And you have to sketch the output if the input were to be a square wave signal. Remember that this is an integrator. So all you have to think about is that what happens if you integrate a square wave. Think about it, okay? Now going to the differentiator, it asks you the same thing. It is asking you for a time domain equation for the output in terms of the input. So you can go back to the differentiator. You can say that you're operating it at lower frequencies, and you can make it look like this. And this is just a differentiation of the input with multiplication with a specific constant. Okay. And rest is the same. You find the resistance value, you plot the Bode plot. When you're trying to plot the Bode plot, use the actual transfer functions, not the approximated ones. Okay. All right. And then for the finite gain bandwidth limitations. So now you're using a non-inverting configuration. Remember, you already have an open loop op-amps Bode plot. You're using a non-inverting configuration with 3 different gains. You just have to plot how the Bode plot looks like. Find the transfer functions, guess the Bode plots. For the unity gain buffer, which is this, right? The buffer, which is a voltage follower, correct? Find the transfer function, and then if the slew rate of the op-amp is this is actually the slew rate of US741 from the datasheet, if you remember. Find the maximum frequency given an amplitude, right? And find the maximum amplitude given a frequency in the slew rate. Okay. All right, that's your calculations. And then you have a lot of simulations, which I believe you already did. You did the AC simulation, transients, right? But there are a lot of them. So just make sure that you have a lot of screenshots, all the values documented. And measurements are also a lot of them. So I highly recommend that you come prepared to the lab with the circuits plugged in, okay? And so that you can finish in the given time. All right. Okay, so let me know if you have any questions. And I'll see you in the lab.